Okay, a corollary to the theorem. So a corollary means a immediate consequence of a theorem. So it's like you have a big theorem and then you have some quick extra consequences that come afterwards, and they're called corollaries. Okay, so here's a nice one. You have, if I have AC, if AC are square and they happen to equal identity, then I can automatically assume that A and C are both invertible and they are each other's inverse. So this is good because remember the definition. The definition of a invertible matrix would say that I need AC is equal to I and CA to equal I. I need both those things to be true. So it turns out that in the case of square matrices, I only need one of these to be true. And then the other one will automatically be true, and A and C will be each other's inverses. Okay, so again, in the case of square matrices, I don't need both equations, I just need one. But the matrices must be square. Let's see an example to illustrate that. So I want you to actually do this exercise, calculate these two things, and tell me what you get. Now, I'll do it. So AC is going to be 2 by 2. So I get 1, and then I get a 0, and then I get a 0, and then I get a 1. So this is I2. Okay, so we have AC is equal to I2. Now we're going to see that CA is not equal to I3. And hopefully you've calculated that already. So CA is not going to turn out to be I3. Okay, so if the matrices are not square, then AC equaling I does not tell you anything. Okay, I cannot conclude that CA is also going to be I, and I can't say anything about A and C being inverses of each other. Okay, another corollary. This one's fairly straightforward. So if A is invertible, what does that mean? Wow. We've already seen that A is invertible if and only if A can be reduced to I by row operations. Now, if you think about I, how many pivots does it have? Well, it's going to have these pivots down the diagonal, and pivots. Okay, pivots are also known as leading entries or leading ones in this case. So the rank equals n. I have a pivot for every row. So rank of A does equal n. So nothing fantastic there. In fact, you could, if you were so inclined, you could take this statement here and add it to your invertible matrix theorem. If you feel like doing that, you can throw it down right here. You could have part 6, rank of A is equal to n.